All right, we're going to talk about exercise metabolism to kind of give you an idea of some of the measurements we make in the lab. This is a sneak peek at exercise physiology. Some of these slides come directly from my class, so they might be familiar, or you might get to have a preview of what you might learn sometime. But mostly we're going to talk about these different exercise intensity domains. A lot of times we describe exercise as high intensity, low intensity, or you might have heard the term VO2 max. We can actually break up exercise intensities into 4 discrete exercise intensity domains where you have very distinct physiology when you're exercising at these different intensities. So let's look at it. So first, let's talk about what the different intensity domains are, and then we'll go in and discuss what the physiology of each of these intensities are. You'll learn a lot about some key measurements that we make in the lab. For example, maximum power. We assess maximum power with a Wingate test. We assess VO2 max quite often on the bike, and critical power is another one that we assess a lot. You'll figure out what these things mean. So whenever you exercise, in order to perform work, you need ATP. That ATP is utilized to move the muscle. So we have ATP. I like to think of ATP as a battery. It has stored energy or potential energy. That ATP is then broken down by the muscle to facilitate the movement of actin and myosin and cause a muscle contraction. Now, the problem is we don't store a lot of ATP, very little. We have to recycle our ATP. Once it's broken down from ATP, it becomes something called adenosine diphosphate and an inorganic phosphate. They're separated. We only have enough ATP stored to last us just a few seconds is all. So it's important that we recycle it. And a lot of what we measure in the lab is how quickly you can recycle your ATP. We have 3 ways to recycle our ATP. First is with phosphocreatine. Second is with glycolysis. That's the rapid breakdown of carbohydrates that often forms lactate. And the third is our aerobic metabolism, which requires oxygen to fully break down carbohydrates or fats. Now, there's this really interesting relationship between the power that you're exercising at and how much ATP you're using and how long you can sustain it. So if you're at a low intensity, you're using only a little bit of ATP per minute, right? You're not doing a lot of muscle contractions. And that results in very high sustainability. This axis over here tells us how long you can hold something. As you get to really higher levels or higher intensities of exercise, the sustainability drops. And around the same time, how much ATP you require bumps up. The maximum power that you can reach on a bike, let's say you do a Wingate and you find out that it's about 740 watts, you could only hold that 740 watts for maybe a second or two. So you can't hold your maximum ATP resynthesis rate for very long. Now, what we use is oxygen consumption. Oxygen consumption or aerobic metabolism is how we get ATP sustainably. We have these other anaerobic mechanisms, phosphocreatine, glycolysis, that provide us with ATP, but they're not very sustainable. We only use those when we're in desperation or accelerating is kind of what I like to think about it. If you're starting to move faster, right as you're accelerating, you use these anaerobic mechanisms. But if you've been going for a while, you definitely need oxygen consumption. And that oxygen consumption at the level of the mitochondria results in the resynthesis of a lot of ATP. It's a little slower, so you don't get a lot of ATP every second, but you get ATP for a prolonged period of time. So the intensities that you can sustain with aerobic metabolism, or a VO2, are lower. It's not your max power, but it's a power that you can go for a long time. So how do we measure VO2? O2 represents oxygen, V means the volume, and if we're going to be technical here, there should be a dot over that. So the V means volume, but the dot means a rate, the rate at which the volume is consumed. So we hook up a person onto the bike. Person's just on an exercise bike, and here we have them breathing into a mask. All their exhaled air goes in there. We plug the nose with a clip, and their exhaled breath goes through this little tube into a monitor that's attached to a computer. The monitor measures how much oxygen is in the exhaled breath. We know how much oxygen is in the room air, and if we measure how much oxygen is in their exhaled breath, we can tell how much they've consumed. And now here's what happens. As we start this person off at a low intensity exercise, let's say about 75 watts, they require about 0.75 liters of oxygen every minute to do that work, to do that power output. If we increase the intensity, now they're at 125 or something, you can see the oxygen consumption has gone up. Why has oxygen consumption gone up? Because they're contracting their muscles more. That contraction requires more ATP, and more ATP required means you have to resynthesize more by aerobic metabolism or oxygen consumption. So if you keep increasing the intensity, the VO2 keeps going up until you get to this point where further increases in intensity or power output fail to elicit an increase in VO2. Right? If we follow this trajectory, at 200 watts, this person should be consuming about 3 liters, but they don't. When they hit about 150, they start to plateau. This point here is their VO2 max. It's the most oxygen they can consume per minute for a given exercise, in this case, cycling. Now, if they had better oxygen delivery or more mitochondria to consume the oxygen, they might achieve this, but they don't. We're increasing the power output, meaning we're increasing the ATP demand, but they're not able to consume more oxygen and resynthesize ATP aerobically. So we get this deficit here, right? If all the ATP was being resynthesized aerobically, they should be right here with oxygen consumption, but they're not. They're way down here. So something has to make up this difference between what is needed to do 300 watts or 200 watts and what they're actually getting. And this is where those other metabolisms come in, those anaerobic metabolisms. So to make up this difference of what they can do aerobically and what the amount of ATP that's needed, you kick in these anaerobic systems that aren't very sustainable, and so they fatigue, right? So now the VO2 for a given intensity of exercise or given power output is very predictable. It doesn't matter if you're trained or untrained. If I put you guys all at 100 watts, you should all have a VO2 right around here. If I put you at 150, you should all be here. Submaximal VO2 is very similar for power outputs. But what happens is that people who are endurance trained can reach higher VO2s. See, this line continues very predictably up even for elite athletes. So there's this pretty standard relationship between power output and VO2, where it's somewhere around, oh man, it's like somewhere around a liter of oxygen for every watt, for every 100 watts or something like that. It is a decent estimate. Now, the VO2 max, or the maximum oxygen consumption they can achieve, is different for each of these people, right? This sedentary person here, this active person here, this endurance athlete way up there. But so the difference here is that at 300 watts, this endurance athlete can probably sustain 300 watts no problem because it's well below their VO2 max. Whereas this sedentary person, their VO2 max is right down here at about 200 watts. If you put them at 300 watts, they might be able to pedal for a few seconds, like 30 seconds, fueling that exercise anaerobically with phosphocreatine, but they won't be able to do it very long. All right, so VO2, very predictable, and we're going to use this a lot to determine how intense an exercise is. So we have these different exercise intensity domains. And here's just a bit of terminology that we'll use to separate our domains. First of all, On this diagram, I want you guys to understand this diagram pretty well. The y-axis represents how much ATP is being consumed and resynthesized. So the dashed line is how much ATP is required to do that intensity of exercise. And then the colored in portions represent how that ATP is being made or resynthesized. Blue is from oxidative phosphorylation of fats. Yellow is oxidative phosphorylation of carbohydrates. Whoa, this diagram's bad, guys. Sorry, let me relabel this. This is going to be, the blue is oxidative phosphorylation of carbohydrates or fats. This is just aerobic metabolism. Sorry for the error. The yellow is not oxidative phosphorylation or aerobic metabolism. The yellow is glycolysis. And then the red is phosphocreatine. So when we're at these lower intensities, we're meeting our increased ATP demand by consuming more oxygen and resynthesizing more ATP aerobically with the blue. We get to certain intensities where we then, the ATP resynthesis rate of the mitochondria and that aerobic metabolism, it's not fast enough to get enough ATP by itself. So right in here, we start to recruit anaerobic glycolysis, or the rapid breakdown of carbohydrates, and we'll start to form lactate. Then above that, if we keep going to higher intensities, now both aerobic metabolism and glycolysis they're not enough to get enough ATP, and now we need to go into our major emergency store, our absolute desperation, phosphocreatine, right? So lactate threshold, if we increase exercise intensity, lactate threshold is the point where we start to have a much greater reliance on this glycolysis. That'd be right here. Can you see how we have yellow coming in here? So once you start to use this glycolysis, lactate is produced, and that shows up in the blood. So the intensity where we see a lot of lactate getting in the blood is the lactate threshold. Anything below lactate threshold, we term moderate intensity exercise. Anything between what we call lactate threshold and critical power is something called heavy intensity exercise. Now, critical power is the highest power output where you can get a steady state heart rate and VO2. Normally when you exercise, if you're at a moderate intensity, I'll show you this in a second, if this is VO2 or heart rate, as you start to exercise, it'll go up and then hit a plateau. Now, if you get to a really high intensity above critical power, it'll go up and keep going up until you fatigue. Critical power is the highest power where you can get this steady state, where your body can get used to something and sustain it. Okay. So anything below critical power, between lactate threshold and critical power, is heavy intensity exercise. And then between critical power and VO2 max, which we've already talked about, is severe intensity exercise. An important thing here with severe intensity exercise, we're relying on aerobic, glycolysis, and phosphocreatine. And another thing, any intensity in severe intensity exercise will lead to the achievement of VO2 max. If you go long enough at this power output right here, because you can't get a steady state, your VO2 will keep going up and up and up until you hit VO2 max. VO2 max is only achieved during severe intensity exercise. Then the extreme intensity exercise, which is heavily reliant on phosphocreatine and glycolysis, it's so fast and brief that you can't achieve VO2 max. And your maximum power, something you can hold for only 1 or 2 seconds. All right, let's talk about how we determine these. So moderate intensity exercise. When we start exercising, I mentioned this again already, we go from rest to exercise, and there's an immediate increase in ATP demand, right? Your muscles are immediately consuming ATP. Now, it takes a while for your breathing to get up and running. It takes a while for mitochondria to get up and running. And so there's a delay. You don't meet all of your ATP demand right away with oxygen, with aerobic metabolism. We have this gap here between ATP being consumed and ATP being resynthesized aerobically. That gap here, this is filled in with anaerobic metabolism like phosphocreatine, a little bit of phosphocreatine, and anaerobic glycolysis. So we have a small, this is called an O2 deficit. We have a small deficit, but what's important here is that as the VO2 gets up, you eventually hit a steady state here. And that you'll hit steady state in moderate intensity exercise within 2 to 3 minutes, right? So your heart rate will be steady throughout, your VO2 will be steady throughout, whether you're at 3 minutes into the exercise or 30 minutes into the exercise, the VO2 or the heart rate should be roughly similar or constant. Now, moderate intensity exercise is extremely sustainable because we're using this aerobic metabolism, which is very, very sustainable. You can go on for a long, long time. This is like walking or jogging at a slow pace. We're talking hours. If you go on a hike, chances are most of the hike you're at a moderate intensity exercise. Okay, so we have our maximum duration or sustainability way up here. Below lactate threshold, you can go for a long time. And part of the reason is because we're almost exclusively fueled by aerobic metabolism. Now, what about heavy intensity exercise? Heavy intensity exercise differs a little bit. If instead of being like at 100 watts, let's say now we're at 200 watts for this heavy intensity exercise. So our ATP demand has now gone up. We need this much ATP to do our heavy intensity exercise, or 200 watts. But we can't get all of that ATP aerobically. Right? So we're going to have the aerobic metabolism increase. Notice something here. We still have this big O2 deficit, and that O2 deficit persists throughout. Because we're above the lactate threshold, we know that we have anaerobic glycolysis contributing to our ATP. And so whether you're 2 minutes in or 40 minutes in, if you're in this heavy intensity exercise above lactate threshold, you have both aerobic metabolism, probably a lot of aerobic metabolism of carbohydrates, and anaerobic glycolysis going on to meet your ATP demand. Another important point here, besides not getting all of your ATP exclusively from oxygen consumption, right? We always have this yellow or the glycolysis. Another important point is that we don't hit steady state right away. You can see if this was just a normal moderate intensity exercise, we would follow this curve here and we'd have that plateau. That's not what we see in heavy intensity exercise. You have something called a slow component, where first you have this fast component that your VO2 increases rapidly. So this would be the fast component, and that's in any intensity of exercise. But now we have this slow component here, where you have a gradual increase for a few minutes after that. And this slow component in heavy intensity exercise, so between lactate threshold and critical power, that slow component will eventually hit a steady state. So after about 10 minutes or so, you'll finally hit a steady state where your heart rate is finally constant, and it will stay that. Your VO2 is finally constant, and it will stay that. Whether you're 30 minutes into the exercise or 60 minutes into the exercise, you should have about the same VO2. You're no longer on this slope here or this slope here. You've hit a steady state. And steady state represents something you can sustain. So what about the lactate threshold? If we measure how much lactate is produced by your muscles and shows up in the blood, if we start at a low intensity exercise, moderate intensity, you'll have very low lactate levels as we increase. But then you'll suddenly get to a point where somewhere around 60% of VO2 max usually, you see an exponential increase in how much lactate is in the blood. And we just determined that usually by doing a little finger prick like you'd see for a diabetic, checking their blood sugar. Really similar process, we just check the lactate in the blood. And so this point here where we start to see a lot of lactate showing up is the lactate threshold. And the lactate, we're not going to get into this. This is a little too in depth for what I care that you understand. It's coming from anaerobic glycolysis, the breakdown of carbohydrates, the rapid breakdown. Let's skip through this. You guys don't need to know that. All right, so how long can you sustain heavy intensity exercise? So exercise intensities between lactate threshold and critical power, you can sustain for several hours. This is the intensity that you would be running a marathon at. And marathon runners are well above their lactate threshold. So you'll see plenty of lactate or plenty of yellow here. But the majority of their ATP is still coming from aerobic metabolism. So if you're in this intensity here, in this heavy intensity, we're talking anywhere from like an hour to 2 hours minimum is what you could do, as long as like you don't get bored and you keep refueling with carbohydrates. But notice when we go to the next one, that sustainability drops, and that's why critical power is so important. This is severe intensity exercise. Now in severe intensity exercise, if we look at how much ATP is being consumed and produced, we have a really high ATP demand. This should be greater than whatever the moderate intensity units were. And in severe intensity exercise, this is how much ATP we need, and this is how much we can get from aerobic metabolism, right? So we get a lot of ATP from aerobic metabolism, but not nearly all of it. And we get quite a bit from anaerobic glycolysis and phosphocreatine. I'll show you that in a second. So you never get all of your ATP in severe intensity exercise. You never get all of your ATP. This is severe. Man, this slide, I must have used an old slide for this. Severe intensity exercise, you never get all your ATP from aerobic metabolism, and you'll get a contribution from glycolysis and from phosphocreatine. Now, another key indicator of severe intensity exercise is that we never get a plateau here. The VO2 and the heart rate never go flat. They're constantly climbing. That slow component never goes away. The VO2 keeps going up and up and up and up until you fatigue. The heart rate keeps going up and up and up and up. So if you're exercising, if you're like running and you have one of those heart rate monitors on, you're looking at it as you're exercising, if you're in severe intensity exercise, you keep the same speed, let's say 5 miles per hour, you run that 5 miles per hour the whole time. If it's severe intensity for you, your heart rate will keep going up and up and up. It doesn't matter that you're doing the same speed. At severe intensity exercise, your body is so strained that it cannot reach a steady state. It can't get used to what you're doing. And this is the key indicator of this is the critical power. Now, critical power is the highest power output that you can achieve a steady state VO2 or a steady state heart rate is a good estimator of that. Anything below critical power, you'll hit steady state and you can sustain. Anything above critical power, you won't hit a steady state. Your heart rate will never settle down. Your VO2 will never settle down. In fact, above critical power, the heart rate and the VO2 will keep going up and up and up. And if you keep going until you fatigue, the point you fatigue at will be your max VO2 and your max heart rate. Most likely max heart rate, definitely max VO2. So any power output, whether it's right here, let's say this is 300 watts and VO2 max during a graded exercise test gets you at 400 watts, whether at 300 watts or 350 watts or 400 watts, if you keep going until fatigue, you will reach VO2 max. Now look at this. This is another key point about critical power. If you're above critical power at a power output, if your critical power is 300 watts, if you go at 305 watts, your sustainability is somewhere around 20 to 40 minutes, just barely above critical power. You can only go 20 to 40 minutes. If we go just barely below it, to where instead of being at 305, now we're at 295, so just very small differences. Sustainability can go somewhere around 2 hours, right? So this is a huge threshold for how sustainable an exercise is critical power. And part of the reason for the difference in sustainability is above critical power, we're becoming increasingly reliant on phosphocreatine. We need that phosphocreatine to resynthesize the ATP to meet our demand. And you only have a little bit of phosphocreatine. So once that phosphocreatine is used up, you're fatigued and you can't go anymore, right? So that's why things above critical power, you can't sustain for very long. And it's amazing, this threshold, right? A difference, just changing the power output by less than 10%, by 10%, let's say, can have like a 200% impact on how long you can sustain it. If you wanted to run a marathon and you decided to run, you want to run it right around your critical power or just below it. If you make the mistake and go like 1% over your critical power, you're not going to be able to finish that marathon. Your sustainability is too low. This is why critical power is important. And any power output above critical power, if you can sustain it long enough, will reach VO2 max. So we already talked about how sustainable severe intensity exercise is. What kind of exercises are we talking about? This would be like doing a 1 mile race. In terms of duration, severe intensity exercise at a maximum, somewhere around 20 to 30 minutes maximum sustainability, with a minimum sustainability 3 minutes. And the reason I say 3 minutes is because severe intensity exercise, in order for it to be classified severe, it has to reach VO2 max. And it takes about 3 minutes for the mitochondria and everything else to get up to max. If you can't sustain it for 3 minutes, if you fatigue before you reach VO2 max, now we're in something called extreme intensity exercise. So VO2 max is only achieved in severe intensity exercise above critical power. Now, one more example of how long severe intensity exercise can be sustained. In this study by Burnley in 2012, they had individuals do different percentages of their maximum knee extension. So here they're doing a knee extension exercise, and they had them just kick as many times as they could at different percentages, right? So they're doing 100% of their 1 rep max, or 80%, 40%, 60%. And what you can see is, by definition, the 100% of their maximum voluntary contraction, or 1 rep max, they can only do once and can't sustain for very long. And about 50% they could sustain for a couple minutes. But right here, they measured the critical torque, or critical power. It's another name for critical power. If they were above the critical power, an intensity above it, so here their critical torque is somewhere around 32%, I think. If they're at 33%, they could only go for about 25 minutes. But if they went to 31%, now they can go for about 45 minutes. And if they're at 30%, in this study, they actually went over 60 minutes. They stopped them at 60 minutes because they didn't want to wait around for people to fatigue, because below critical power, it takes a long time to fatigue. So you can imagine, if you have a high critical power, you have good endurance. Now, what's important here, I'll draw it here, is that a person's critical power, how close it is to their VO2 max, varies. So if your critical power is here, really close to your VO2 max, that means most of your VO2 max is sustainable. So if your VO2 max happens at 300 watts in a graded test, then your most of like 280 watts, your critical power, that means you can sustain a very high intensity of exercise. What if your critical power, oh, come on. What if your critical power was way down here? It means all of this stuff is not sustainable, right? So people with the same VO2 max can have different critical powers. It varies quite a bit. In general, it's somewhere around 50 to 70%, but that could be a big difference. Some of these elite athletes, it's up to 90%. So that means 90% of they could run at 90% of their VO2 max for a couple hours, right? So the higher your critical power, the higher that threshold for fatigue. It takes a higher power output to fatigue you. Now, extreme intensity exercise is even above VO2 max. It's a power output that you can only do for under somewhere around 2 to 3 minutes, down to 0 second, like down to 1 second. And with that with extreme intensity exercise, the power output is so high and the exercise is so brief that you don't have enough time to achieve VO2 max. As illustrated here, let's say we're exercising, let's start at max power, that's easiest. At max power, we're talking 1 second of exercise. We don't have enough, that's not enough time to get a lot of aerobic metabolism. So almost all of your ATP at max power is coming from phosphocreatine. If we decrease the power output down to, let's say right here, still an extreme intensity exercise, we have some coming from aerobic metabolism, a lot from glycolysis, but the majority still coming from phosphocreatine. So if we looked at what's going on with the VO2 here, and in severe intensity or extreme intensity exercise, let me draw this VO2. Your normal VO2, if you're going to hit max, is going to go up, and then here's VO2 max. What happens in extreme intensity exercise is that you're on this trajectory to hit max, but you fatigue, your muscles give out, your brain gives out, something gives out before you can hit it. And so you stop at this point or this point, well below your VO2 max. Severe intensity exercise has a very high ATP cost, where here we have a lot coming from phosphocreatine. Some of it comes from anaerobic glycolysis, and then we'll get some from aerobic metabolism. A key factor here is after the exercise is over, you start to breathe. Have you done this? If you do a 100-meter sprint, that's almost all anaerobic metabolism. It's almost all phosphocreatine for a 100-meter sprint. But after you do that sprint, or after you sprint down the basketball court once, you're breathing heavily, right? And that's what we call an epoch. After you burn all that ATP and burn all that phosphocreatine, you need to resynthesize it. And that happens with aerobic metabolism. So after you exercise, after you do your sprint, you're going to be breathing heavily and you'll have a lot of aerobic metabolism going on afterwards. Now, maximum power, how do we determine it? We put someone on a bike in a Wingate test, and we have them sprint for about 30 seconds. And the faster they pedal, the higher the power output, and they'll hit a little peak. If you start them sprinting, they'll go up for the first second or two, and then everything will start to come down. Their power output, their pedaling speed will go down. They'll go slower and slower. And so this would be their max power. That they could, the highest power they can achieve over 1 second. And normally when we determine max power, we just have them go for about 30 seconds. So in the lab, we'll do Wingates for about 30 seconds. But an interesting thing is if you keep them sprinting for 3 minutes, as long as they can, it's ridiculously difficult, but if you can keep them pedaling as hard as they can for 3 minutes, this power output where it starts to plateau, this is pretty much identical to their critical power because it's a sustainable rate of ATP consumption and resynthesis that doesn't heavily rely on anaerobic metabolism. All right. So extreme intensity exercise between the maximum sustainability is about 2 or 3 minutes. This can range from 1 second to maybe 2 or 3 minutes. And the difference between severe and extreme intensity exercise is in extreme intensity, you don't have enough time to get to VO2 max. If you hit VO2 max, by definition, it is severe intensity exercise. All right, these different exercise intensities will have huge implications on the physiology. As you can imagine, moderate intensity exercise doesn't put a lot of strain on your system. You're not going to get a lot of acid in the muscle. You're not going to be breathing very heavily. You're not going to put strain on the heart. And so exercise training at moderate intensity doesn't seem to elicit a ton of adaptations. Heavy intensity exercise, now we're getting a little more serious here. You can do it for a prolonged period of time, so like 40 minutes to 2 hours. And so you can get adaptations here, but you're not going to get super acidic. Fatigue and heavy intensity exercise usually comes because of central fatigue or brain fatigue. You just get sick of it and your brain tells you to quit. Or in heavy intensity exercise, you also just run out of fuel, carbohydrates typically. And so if you keep refueling with carbohydrates like Gatorade, you can probably keep heavy intensity exercise going on for several hours. Now, severe intensity exercise, the reason people fatigue here is because of peripheral fatigue. The muscle gets way too acidic. The muscle can't contract anymore. It's not the brain telling your muscle to stop. It's the muscle being incapable of going anymore. The brain's saying, go, 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 go. But the muscle's like, dude, I can't contract anymore. So that's what happens in severe intensity exercise, and same with extreme. Because we don't achieve steady state VO2, steady state heart rate, or acid levels, lactate, epinephrine, we don't achieve steady state in this severe intensity exercise. So we're going to get major stimuli of these things: heat, acid, ADP. All these things are stimuli for adaptation. And so what we're seeing in some of our studies right now is that more adaptation occurs above critical power than below. If you run 5 miles below critical power, you're not going to adapt as much as if you ran that 5 miles above your critical power in a shorter amount of time. So it seems like exercise training, at least in terms of VO2 max and endurance, above critical power seems to be very important. All right, that's all I'll talk about for today. Let me know what questions you have when we see each other in person.